Okay, so I've gotten multiple emails about the test. I tried to put an announcement, and every time I get the emails, I'm not on my computer, so I can't like post on Canvas. I think I removed it so you can't see the old link. The test is not due until the 30th. The test isn't even written yet. That is my to-do list for the weekend, honestly, because that's what I do. Uh, yeah. So it's gonna be a little bit, you're not late with it, it's just not there. If the link is dead, that's why. Yeah, I threw an announcement up, so hopefully we're good there. We're gonna go through 7.3 and part of 7.4. And then once my notes are done, we're done. We'll see where we end up. So 7.4 had a lot of stuff, but we were missing a piece to make it make sense. So I'm going to give us the missing piece today, and then we'll do, today's Wednesday, right? Yeah. Then we'll finish it with the actual stuff that's in that chapter or in that section on Monday. And I think that's the end of 7. So that'll be the end of our material for the next test. But yeah, I don't know when they introduced this type of probability, but it wasn't in this chapter, and they talk about it like you should know it. So we'll talk about it. I like this sort of probability, but we've discovered that the things I like, you all don't like, so that's okay. Um, yeah. 7.3 we're looking at is your data normal? And we do this when we have a small data set because there's not enough like data values to really get a good feel for it. So we kind of have to squint at it and say, okay, is this working like a normal distribution, or do we throw it away? So I said definitions on slide 75. Apparently I didn't feel like writing them down today. Sounds like me. 75. Okay. Oh, and it disappeared. So here's our two definitions. I am not going to write them out. I've been writing all day. My hand is tired. We have a normal probability plot. It is a graph that plots the observed data values and their normal scores. So there's, I think it's their z-scores. Yeah, it's going to be their z-scores. And then your normal score is what we expect the z-score to be. And I'll show you how we calculate that. So two definitions. If you don't, I do have people writing. I'll wait a sec. Problem with just throwing that up there is then I talk too fast. I'll take a drink. I had a professor who, anytime he'd give us a problem to work on, he's like, and I'm going to go take a drink. So he didn't like talk through it and just like walk away for a minute, let us work, and he'd come back. I always think about that. He was weird. Yeah, yeah, except for some personal issues with him. He was an interesting fellow. Okay, the man wore the same outfit every single day of the semester. Same pants, same shirt, same sweater. It was weird. Anyway. All right. At least he didn't smell it. Okay, can I go past that? Everybody wanted to get it? So more than anything, how do we calculate this? Um, I'm not gonna lie, until today, I hadn't even heard about this one. So I got to learn today too. All right, so we're gonna draw the normal probability plot. So drawing the plot. We're gonna draw the graph. So the first thing we're gonna do take your data values and arrange them in ascending order. So you take your smallest one and then your next, da, 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 until you get to your biggest one. These will be small data sets, so this shouldn't take very long. Step 2, we're going to compute this weird little formula. F sub I equals I minus 0.375 all over N plus 0.25. Your I is the index. We call it the index. It's the position of the data value. So is it the first data value we listed? Is the second? Is the third, etc. And we're going to do an example of this because this is weird. So it's our index, our counting. Our N is our number of data values. N is almost always our number of data values for us. So your I should go from 1 to N. Your F sub I, when I was looking through the notes, they didn't tell us what F sub I was until like 3 pages later. So it is the expected area or the probability to the left of our given data value. So when we draw our normal distribution, if this would be our data value, F sub I we calculate is this area. It's our probability. Okay, once we have all of our F sub I's, we're going to do this for each data value, down the line. Then I will not be able to fit that word down there. Our Z-score chart we had last time, we're going to use it backwards like we did at the end of the class. So we'll look at our F sub I, find it on our chart, and figure out what our Z-score should be based on that. And finally, we're going to plot our data where our X is our data value. That looks really weird. So the stuff we arranged in step 1, those are our X's. Our Y's are going to be the Z-scores we found in step 3. So 1 and 3 tells us where they come. And then, once we have our happy little plot, make a list of your X's and Y's. Then we're going to run a correlation coefficient on our data and decide if our data is linear or not. If it's linear, it's normal. If it's not, it's not. So use correlation coefficient. To decide if data from 4 is linear or not. And how we decide if it's good enough is there is a table, and I will show us where this is. In appendix on Pearson. Okay, so the table 5 is our Z-score table, which I gave you a copy of from a different place. Table 6 is the table we're going to look up for our R values. Let me show you where that is because I'm going to need to pull that up anyway. It's buried deep in Pearson. Okay, I see people writing, so I'll give a sec. There is a StatCrunch way to do this. Homework will tell you how to do that. I'll show you the analog way. We good? I don't want to like fly by stuff. All right, so I'm going to go to Pearson. Yes, I know. You always tell me that. Thank you. Now I have to remember where this is. So go onto your Pearson, get into your, so you can see this toolbar over to the left, e-textbook. Click on the top e-textbook again. Really hope this works. It worked on my other computer. Okay, so we're here, we're in our book, go to the table of contents. There might be a shorter way to get here. This is how I figured out how to get here today. Oh, I already flipped there. So under a table of contents, you can go down the appendix, tables and formulas. 4, or excuse, I don't know. Table 5 is our Z-score table. I gave you a copy of that so you can use it or not, or this one. Table 6 is this guy here. We'll come back to that in a little bit, but I wanted to get it pulled up anyway. We're going to need it. So we'll get there in a sec, but that's how you find it. It's buried. Okay. My data is on page 81. I should have written my data down. Alas, I did not. Oh, don't hit buttons. Okay. This is just a data set from the slides, nothing really special about it. No, stop it. Okay, so here's my data set, 31.35, 32.06, 3191.91, 32.52, 31.26, and 32.37. Hopefully you wrote down steps because scrolling back and forth is going to be terrible. The first thing we want to do is take this data and rearrange it. I want the smallest value on top, the largest value on the bottom. All right, 32's 32.06. U 32.37, 32.52. Okay. Rearrange our data. Next thing I'm going to do is kind of not necessarily listed. I'm going to index these just so we don't have to keep counting and asking. So this is data value 1, 2, 3, 4, 5, and 6. Nothing magical there. So it also tells me my N is 6. Now we need to get our F sub I column. So that little F sub I equation, let's look at F sub 1. So our first one will be F sub 1, second one is F sub 2, down the line. So F1 equals, we take our index, which is 1 minus, oh, really? 0.375 over 6, which is our N, plus 0.25. The denominator is going to be the same for all of these. So 1 minus 0.375 divided by 6.25. I get 0.1. All right, now I'm going to do the next one, except instead of 2, I'm going to plug in, or excuse me, instead of 1, I'm going to plug in 2. So I take 2 minus 3.75 divided by the 6.25, because the denominator does not change, 0.26. Now I'm going to plug in 3 instead of 2, and I'm going to stop talking about it and just do it. Oh, neat. Okay. Okay. Are we all okay how we got our F sub i's? Okay. That's the weird step to me. Okay. Now we're going to go to our z-score table. So it's either table 5 or the handout. I guess I didn't give that to you. I just showed you where it was on whatever it was. We're going to look these data values up. I'm going to scribble these down on my sheet so we can find them easier. If you have access to it and want to help me out by looking for some of these, that would be great. Well, you all have access to it. Why is this quote so short? All right, so the first 3 numbers will be on the negative side. The second 3 will be on the positive side. All right, we're going to look for 0.1. It looks like the negative 1.2 and I think negative 1.28. Is anyone there looking at it? This number is, whoops, no, don't highlight everything. This number is as close to 0.1 as I'm going to get. Adjusting either direction isn't going to help. So that corresponds to my z-score of negative 1.28. We good with that one? Okay. Now we're going to look for 0.26 on this chart. That one. So I'm between 0.2611 or 0.2578. I feel like 2611 is going to be slightly closer. It's 11 off versus 22 off. So that goes to negative 6.4 or 0.64. I can't read. Okay. 42. You tell me what our best 42 is going to be. I think 0.20 will be slightly better. Are you talking about the first column? Yeah. I figured that's what you were assuming. So, yep, you're right, that one. All right. Now we go to 5.8, which is on the other page. Now we're going to look at the top. What's our best 0.58 number? To me, it looks like this guy. Okay, that's 0.20. What do you want to bet 74 comes at 0.64? Yep. Hey, it's a nice mirror image. 0.9 is going to be 1.28. So you get the negatives. It's a mirror. You're going to get the positives. Just works out nice like that because it's normal. Ouch. Why didn't I say? I'm kicking myself for not having written down a formula we're going to need. Okay. So my z-scores, I'm going to erase these so I can scoop this over. I get negative 1.28. It's an 8. Negative 0.64. Negative 0.20, 0.2, 0.2, 0.64, and 1.28. Those are the numbers we all agreed on from the previous thing. I just translated them over now. Okay, so if this is normal, this is what we'd expect our z-scores to be. So nice and even. All right, now I have to plot this, and I don't have a nice way to do that. I'm going to break a forbidden rule that I hate breaking. I'm going to skip some X data values here. I'm telling you I'm breaking this rule, this bad rule, because all of my X values are like between 31 and 32 and a half, pretty much. So if I were to do this squished, it tells me nothing. So I need to spread them out. So I'm skipping some stuff so we can get to what we care about. I put a little there to tell me that. All right, so 31, 2, 3, 4, 5, 6, 7, 8, 9. I need more space in this. 31, 2, 3, 32.1, 2, 3, 4. Okay, good enough. Push my data values in there as best I can. With my Y values on there as best I can too. So I'm gonna go from by 0.5s up to 0.5 and negative 0.5. That'll be good enough for our purposes. This is just a sketch graph. All right, so my first data value is 31.26, so here-ish, and we get a negative 128. So here is my first ordered pair. Second one, I get 31.35 and 0.64, so we'll call it here. Next data value is did I put them in the right spot? Yeah, 31.91, so here-ish, and I'm gonna go to 0.2. Okay, then I get 32.06 and I go up to 0.2. 32.37, 1, 2, 3. And I go up to 6, 4 here-ish. And then finally 32 and a bit, and I go up to 0.128, which is here-ish. Plot your data values. At this point, we would use our correlation coefficient to decide if this is a good value or not. I didn't write that equation down, so I'm going to steal it from the other page, and then we'll look it up. This is roughly 91. Really? There's how they plotted it. I don't like it because the axis is in a weird spot, but whatever, it works for us. They go through and they find that our correlation with our data values is 0.888. Now we have to decide, is this good enough? So how we decide that is we go back here, we go to our tables, and now we look at this guy over here. Or no, sorry, I switched it. So our sample size is 6. Our critical value is 0.888. So our other number was what we should have used. Scribble that down too. Okay, our data value is 0.970. So we take the critical value, which is 0.888. So our observed Y value, the Y value, or excuse me, R value that we found with our data is 0.970. the critical value, so we call this R crit, is 0.888. In this case, we're always putting our data as ascending, so we'll always get a positive, which is nice in this case. If R observed is greater than or equal to R crit, our data is normal enough. Our data is going to act like it's normal. We're good. So we can say, okay, we're going to treat this as a normally distributed data set because the correlation's good enough. So in our case, this is the one we found, or we pretended we found, it is bigger than the critical value. So for us, data R equals 0.970, which is greater than 0.888, which is our critical value. So our data is close enough to normal that we're going to pretend that it is. We're going to accept it. So anytime you have a critical value, you want your data to, your observed data value to be generally bigger than that. Unless it's negative, then it'd be smaller. But most of the time, it's just going to be bigger. We call it a day. All right. That's 7.3. 7.4 is binomial probability. So they just jump in saying, hey, this is how we know binomial probability is normal. What's binomial probability? We don't know that. What? No, but it's a weird little thing. So to have binomial data, it's all about the coefficient really. We have to have we're going to have our trial or our experiment run n times. Every trial, the probability of success is the same. So if our probability is 0.38, for the first trial, it has to be 0.38 for the 80th trial. It has to be the same value all the way through. Each trial is independent. So the outcome of whatever happens in the first one doesn't affect the outcome of the last one, which helps our probability stays the same. And every time we have two outcomes. We either succeed or we fail. And if we have an experiment where there's really like 8 different outcomes, we're going to say these outcomes are successes, anything else is a failure. So we can define that special so it works out like we need it to for this. We want X successes. So we have to fit these criteria to use binomial probability. And it's I think it's kind of neat. When it works out very nice. Our equation probability of X success equals our number of trials, N, times the number of successes that we want or choose. I will explain that notation in a sec. The probability of success to the X power, 1 minus the probability, so the probability we fail, to the N minus X. The number over number with parentheses, I forgot we used a different notation. That is our combinations, N choose X or N choose R is what we were calling it before. So that's why I don't like that they changed their notation, because this is slick, it's nicer. So remember this equation. N minus X times X. Are we okay with me using the N over X notation? Okay, that's called a binomial coefficient. I could go into that, but I have a feeling you don't care. So if you really want to hear that story, I'll tell you later. If not, we're just going to go with it. That's why it's called binomial probability, because it's a binomial coefficient. Okay. Let's look at an example. Can I scroll past that? Okay. We have a thing we're doing our experiment 4 times. So I don't know what we're doing. We're just doing it 4 times. And our probability of success for every trial is 0.23. So that stays the same through every single trial. We're going to do this a bunch of times because I want to figure out the probability we have 0 successes. We have 1, 2, all the way up to 4 successes. So we're going to do this 5 times, but it's going to tell us something. Hopefully. All right, so if X equals 0, because I'm going to go in order, the probability we don't get any successes, part of our equation is always going to be the same. 4, choose X, 0.23 to the X. 1 minus 0.23 is 0.77 to the 4 is X. So the parts I wrote in as actual numbers are the part that's going to be the same through all of our experiments. So that's nice. The X is really the only thing that changes for us. So I plug it in. 4, choose 0. 0.23 to the 0 times 0.77. 4 minus 0 is 4. Okay, you definitely want a calculator for these guys because they stink otherwise. Use your NCR button to figure out 4, choose 0. I know that one because it's a common one. So see if you can figure this out. See who showed up at my house. Nobody. Cool. That was earlier. New headphones for my child. keeps breaking his. He takes care of them. They just keep getting smushed in his back. So. And it's just been this semester, so he gets a buy on that. What's 4 choose 0? 1. How many ways can we choose nothing? 1 way. So 4 choose 0 is 1. What's 23 to the 0 power? 1. So the only thing we can't calculate in our head is 0.77 to the 4th. What did we get for that? .35. There's more decimals, but 0.35 is good enough for us. We get to do it again. Depending on your calculator, you can put this in all as 1. Just be very careful with your parentheses. That's what I'm gonna do. Though I know 4 choose 1 is 4. No, it's the combinations, the NCR button. Anybody brave? People who weren't brave, would you have been right? Okay. Maybe somebody new could be brave. It's equals 2. No, if you're not, that's fine. I'm not trying to poke fun. I get it. All right, I'm just gonna write the rest of these out since I know that's what's coming. Any takers for the next one? Again? I'm going to say 0.19, but you're on the right track. Round up that second digit. All right. 2 more to go. I promise you won't have to calculate all of these. There's a method to the madness. Sorry, YouTube people, for the dead air. I didn't feel like pausing it. I'm recording it, so anybody who watches it later just gets to listen to dead air from All right, do I have the next two? Say again? What about our last one? I think it's 0.103. Oh, I'm so sorry. I heard that wrong. Where'd you put, I heard 0.1 and just like, no, that's way off. Okay. Yeah. So we should have probably went out 3 decimals if we'd known that this was going to be so small, but we're going to leave it because it's good enough. Like this is enough for our methods. So if we add all those numbers together, what should we get? Or pretty close to what should we get? Yeah. These are all the possible outcomes. We can have 0, we can have 1, 2, 3, 4 successes. So one of those has to be right. You have confused face or not? You good? The sum of this column of numbers should be 1. Because these are all the possible outcomes. One of them has to happen. Okay. So do you notice how our probability, it's not perfect, but our probabilities start small, get bigger, and then get smaller? Can you see how that's happening? It's not always going to be, and that's what this section is going to be about, is when does that happen when it is nice bell curved. But most of the time, it is going to be your few cases and many cases are smaller probabilities where your middle is a lot bigger probability. And you see that happening when your probability of success and failure are close together. So 0.23 and 0.77 are pretty far apart. But if they were like 0.6 and 0.4, you're really going to see that bell curve there. So that's what our binomial probability is doing. We're calculating. It's saying, okay, if I run this experiment 4 times and I get 1 success, it can be on any of these 4. So that's why we have to calculate it multiple times and add it together. That's kind of what it's looking like. All right, does at least how to calculate this make sense? It is very tedious to do all of them, which is why I chose 4 and not like 8, because I didn't want to do that either. So it's long. If you're curious where the name comes from, because I feel like I should give it to you. If we take a binomial, so 2 digits, and we multiply this by itself so many times, we're going to get 5 choose 0 times x to the 5th plus 5 choose 1 x to the 4th plus, actually I'm doing that backwards, aren't I? It's not really going to matter. 5 choose 3 x to the 3rd plus 5 choose 2 x squared plus 5 choose 1 x plus 5 choose 5 choose 0 times 1. So if we were to expand our binomial, that's what happens. You don't have to know that. It's just a fun fact that you'll probably never, ever, ever need, but I had the need to tell you. So now you know. I think they're fun, but that's okay. All right. I'm gonna leave that for, I need to look at that a little bit. All right, that's where I'm going to leave it. So this is binomial probability, success, failure. You can calculate all of the different in-betweens. Most of the time, when they ask you to calculate, they'll have you calculate 1 or 2, not all of the cases, because it does take a long time. All right, I'm going to stop my video. Let me know if you have questions or issues. I'll be here for a minute. Share and